All right, so do we have any question? Great, so that's good. Now the next topic is, so that was basics of neural networks. Let's see how we can train these. Okay, so just a quick recap, because these will be used like over and over again. Network parameters we just discussed, like these are nothing but like the values in your kernels which we are going to learn. And if this is your filter, then these are the parameters which we are looking after. And the intuition of convolution was simple, like once we have a kernel, we try to perform filtering using that kernel in the input image or the input activation map. So we're just trying to find that pattern. So if there is a perfect match, we'll get high activation. If there is no match, we will get low activation. So that's going on inside the CNN. And again, we can try to visualize this. We saw this earlier, so we don't have to go through this again. Now, this is like a general CNN architecture. We have understood like how to process this image and what exactly this image should be. We have understood like the convolution layers in between, what these feature maps are. We know what subsampling is. And again, we have convolution, we have subsampling, and we know fully connected. And finally, we know that we make predictions. So all this structure, we now totally understand what's happening inside this network. Now, we saw this image earlier as well, where the idea was we split our data into training and testing. Now, this training phase is something when we are actually training the network. So when we train, this training is called learning those kernels. All right. Because when we have learned those kernels, then we can actually use them during testing and extract these features and make predictions. Right. So traditionally, like in classical computer vision, we used to extract features and then classify, but in deep neural network, we are directly feeding in the image. So we are combining these two steps. Feature extraction as well as classification is performed at the same time. Now, the question is how we can train them. So what we need is a loss function, all right? So let me try to explain this. Loss function is something which at any point of time will tell us how good your network is performing. All right. And when I'm saying that how good it is performing, it's based on like what kind of prediction it's making. For example, let's say I have a network F and I send in an image of Apple and I'm using it for classification. If the network says Apple with a high probability, it means the network is doing pretty well. But if it says, let's say something else, maybe fish or something else, then it means it's performing very badly. So based on those predictions, we can actually define a loss function which will give me a number, and that number will say how good the network is performing at this particular state of time, right? So then what we do is, once we have this loss function, we perform network training, which is like, again, learning kernels. We do that using optimization. And when I say optimization, this is kind of, we try to minimize the loss of this network, okay? And what it's essentially trying to do is it's trying to find the best network parameters or the best kernels inside that network, which will minimize the loss of your network. So for example, if your network is saying, given an image of Apple, it's saying fish, so it's performing badly, then what we will do is we'll try to optimize the network or change the weights of the kernel in such a way that it moves towards like Apple instead of saying fish. And then that will minimize the loss. So we can formalize this loss function like this. F is your network. X is the input image, for example, image of an Apple, right? And W is all the parameters of a network. So not just one layer, all the layers and all the kernels. So that's represented using W. So for a given set of network parameters and any input sample, we pass this to the function F and it will make some prediction, right? For example, given an image of Apple, it will say whether it's Apple or fish or something. So that's called network prediction. And this yi over here is the actual ground truth. So if it's an image of Apple, this yi says Apple. Now what we do is we look at this actual ground truth. We call this ground truth. we look at this actual ground truth yi, and we compare this with like what the network is predicting, and we can easily compare these two, and that will determine your loss function. And there are different ways to actually do that. For example, I can just subtract those two values. If it's saying apple, it's apple. I just subtract apple minus apple, it's 0, right? So that could be one interesting loss function. And the loss is 0, which means we are happy. The network is doing pretty good job. Now, what we do is we repeat the same process for all the samples in our training data. So I is going from 1 to n. N is the total number of samples you have in your training set. And then we normalize using this number. All right. So this is kind of an average loss on your training set. Okay, so that's the input network parameters. All right. Now, what we do is once we have this kind of formulation, which can estimate how good your network is doing, we use optimization and we try to minimize the cost of the network. Okay. And the way we do that is we make use of gradient descent. I will briefly go over what a gradient descent is. Okay, so it's a way to minimize your cost function to learn better kernels in your network. Okay, let me give you the intuition behind this. Okay, we do have time. Now, let's say f is your function and it takes x as input. So in case of your neural network, x is an image. But let's try to generalize this and take a very specific case where f is like a maybe one-dimensional function. And we can generalize this to like n-dimensional, where the n-dimensional is like coming from images. All right. So let's say we have a one-dimensional function which operates on x. X is the domain, and x can go from negative infinity to infinity, and fx is the output value, the response of the function. So we are just plotting that. All right. So this is the response. Now, if f is your loss function, then it's kind of saying that when you move in your domain from left to right, your loss is actually going down, then it's coming up, again going down and coming up. So this is a loss curve. So when we are saying that we want to optimize this function f, then what we are looking at is we are looking at this particular point. If we can find this point, the value of x at this point, that's exactly what we want, right? Because this is the loss is minimum. We can't go beyond this, because wherever you go, like negative infinity, positive infinity, assuming that these curves are going up. So this is the minimum of this function, and that's what we are looking after. This is the best our network can do. Okay, so that's called optimization, and you can generalize this to like a neural network as well, where this could be like this could be your loss function, and then taking input from images and the network prediction and drawing a plot like this. So there we want to find this point of minimum. Now let's see how gradient descent can help us to find this minimum point. So you randomly pick a starting point, let's say A1, all right? And then what you do is you just find a gradient, and gradient we have discussed a lot in this course. So gradient in this at this point will be like the slope of this curve, okay? Something like this. Now, if you look at this slope carefully, and if you move along this slope, or rather like opposite of the slope, so you will move like towards the minima, right? So what we do is we find the slope that is giving you the direction where you need to move, and then you take a small step, right? So this is like a derivative, the first term here, so that will give you the angle, and then A1 is the original point, and gamma is like the step size, how much step you want to take. So you can just take this step and subtract this from A1, you will reach at A2. So if you're wondering like why a negative sign here, so if you think about this, the slope of this curve is negative, right? Because it's like in the opposite direction. If the slope were like this, it would have a positive value. So this is negative. So this term is going to give you a negative value, and you have a negative sign here, which means that that will turn into a plus. So you're adding something to A1, and that's why you are moving towards right? From A1, you go to A2. So similarly, you keep doing that. You again compute gradient at this location, and you keep moving. So when you move at this point, then your gradient will be 0, right? That's the gradient, that's the slope. So then you won't move anywhere because this gradient term will be 0. So which means that you have reached the minimum which you actually wanted, right? Now, if you are, let's say, as I said, you start like randomly. So you could have started at this location. Okay. Then again, when you compute slope, then that slope would have been positive, but you have a negative sign, which means that you will subtract the value. Then you will keep coming towards the left. Right? Again, you will reach this point. Now, there are some like drawbacks here because you might have started at this location as well. Then you might have ended at this local minima, which happens a lot when you train your network. But again, if it's like if it's not a very big dip here, so depending upon your step size, you might like just cross this, right? You might have jumped directly from this to this point and then keep coming. So of course, like it's hard to like say what will happen, but that's something which you should know, that you can even end up with like local minima. All right, so if you have a convex function is something where you will not have like multiple minima. So it will be something like this, a convex curve, right? So then it's guaranteed that you will always get like the actual minima. But in reality, your CNN or whatever network you define, the loss function is not going to give you a convex function, right? It will be a non-convex function. So this is a convex function, but your actual function will be non-convex. So you might find local optimum point. So this is like one-dimensional, but you can easily generalize this to like multivariate or multidimensional inputs. Okay, so now let's see how we can use this gradient descent to train the CNN network. So any question on gradient descent? Because it's a very simple concept, and if you understand it, like I think it will be easier further in the lecture. Okay, so what happens is in a CNN you have n training examples, right? Xi, and then you have corresponding labels which say that, okay, let's say it's classification, then which class is present, and then you have your network. You can say, let's say, feed forward network, or it could be CNN network. We define that using f, and that function f, or that network f, will take x as input, and then you will have some loss function which will tell you at any point of time how good your network is doing. So to do that, that's the function L. You need the input, the training data, you need the actual labels, the ground truth, and then you need the network parameters, which is theta. So using all these three, yeah, the loss function can tell you how good the network is doing, and then we will try to optimize this function using gradient descent. Okay, so I think, yeah, this I already explained you. In this case, you can just assume that this curve is like your loss function, and you keep moving like around this loss by computing gradients, and you stop when you're like at a minimum point. Now let's talk about like some loss functions which are standard, which are used to actually train your network. I think there is a question from Amir. Is that correct that in a very high dimensional space, local minimas don't occur? And does that mean we should not worry about getting trapped in local minima? Why you will not have local minima? And you can have it. It depends upon like what kind of function you have. And in case of neural networks, you will definitely have a lot of local minimas. And but of course, the second point is true. You should not worry about it. I mean, you should worry about it when you are doing research in optimization. But if you are using optimization just to train your networks, then you should not worry about it, because that's altogether like a different research area. People are already working on that, specifically focusing on how your optimizer can avoid like these local minimums. So Amir, did that answer your question? Okay. So cross entropy is a very, very popular loss function, and most of the time when you're doing classification, you're going to use this. All right, and I will briefly also explain like the intuition why this works. So this is the formulation for cross entropy, and again we are summing this over like the entire samples. So we have n different samples, and we are normalizing using n. So this is the formulation. In this case, yi, this is the ground truth. Again, this is the ground truth, and this is the network's prediction. All right, again, this is the network's prediction. So in this case, you can see that we have two different terms. The first term is like for the case when the object is present, so you call like a positive class. The second is the case when the object is not present, so this is a negative class. I will explain why we need these two. So let's say if your class is present, and let's say we indicate that using a 1, and if a class is not present, we indicate that using a 0. Okay, so what you're saying is that, let's say we are talking about an object category apple. So whenever apple is present, then the output should be 1, and if apple is not present, it should be 0. All right, so in this case, if you look carefully, if it's a positive case, apple is present, so this will become 1 because this is the ground truth, so we can easily ignore this, and this will become 1, so 1 minus 1 0, we can again ignore this term. So when it's a positive case, the only term we are computing is log of what your network is predicting. All right, so we are just taking average of that, and there's a negative sign here. Now, if you try to look at the log curve, so log curve goes from negative infinity to infinity, right? And it crosses the axis at 1 because log 1 is equals to 0. So if your network predicts 1, then log of 1 will be 0, which means loss is 0. So that's perfect. That's what we wanted, right? The network did the right job, and the loss value is 0, and we are happy. But if the network predicts, let's say 0, and that's a bad prediction because Apple was present, but the network is saying Apple is not present because it's predicting 0. Then log of 0 is negative infinity, right? And negative infinity, you have another negative sign, so that will cancel each other. It becomes infinity, which means that if the network predicts 0, the wrong class, then the loss is going to be infinity, which is perfect because it's doing a pretty bad job, right? So the loss is a very high value. And again, these two are extremes, but your network might predict like intermediate values, so it will be between 0 and infinity. So if your network is doing good, it will be close to 0. If it's doing bad, it will be close to very high number. So that's the case for a positive case. And let's look at the negative case. So in case of negative case, again, if it's a negative case, which means Apple is not present, your ground truth will be 0, right? So yi 0, you can ignore this term because this becomes 0. 0 multiplied by anything, it's going to be 0. In this case, 1 minus 0, it becomes 1. Again, you can ignore this coefficient here. And this one becomes 1 minus what the network predicts. Now, if you look carefully, if your network is predicting 0, then essentially it's doing the right job because Apple was not present. But if you put 0 here, it becomes 1 minus 0. So that's 1. Now, log of 1 is 0, which means, again, if network predicts 0, we are happy. The loss is 0. But again, if the network predicts 1, which means that Apple was not present, but network was saying Apple is present. So this becomes, again, 1 minus 1, 0, and again the same thing. It's going to give you negative infinity. You take this negative sign, the loss becomes infinity. So that's like a general intuition how this cross entropy works. When you have like a classification problem where you define like your network is predicting 1 and your ground truth will also be 1 when the class is present. That's the positive case. The negative case is when it's not present, everything should be 0. Okay. The other interesting loss function is mean squared error, and this again you can use in many different problems. And you can use this for even classification, but usually cross entropy is used because that works better. But mean squared is useful, let's say, when you're doing video synthesis or image synthesis, right? You're doing some kind of reconstruction. So then you have to compute like at each pixel whether the pixel was predicted correctly or not. So you can compare that with the ground truth, and then you can easily get this loss. So this is called maybe L2 loss, and then if you don't use the square term, that becomes L1 loss. You can just take the absolute value. So you have these two variations. Now, one very interesting thing when you're developing your networks, when you're defining your loss function is differentiability, right? So differentiability, you know, like what differentiation is, but this is a requirement. Your network, every component in your network should be differentiable. Now, if you think about the convolution operation, which is just filtering, it's a differentiable operator because it's just linear combination of some values, right? And that involves multiplication operation, and multiplication is differentiable. Similarly, like your activation functions, the activation functions which we discussed in the last lecture, like sigmoid, tanh, all those are continuous functions. We can easily differentiate those. Now, even your loss function, it should be differentiable because the reason is when you are training your network using this gradient descent, you saw that at each point of time you need to compute the gradient, and to compute the gradient you will have to differentiate the function. But if your function is not differentiable, it won't work. Okay, so that's a very important point to note, and all of these are differentiable. We just discussed that. Now let's try to understand how actually the kernels are being learned, because your networks are like very deep, right? They have multiple layers, and each layer will have some kernel which we want to learn. So before that, let's first go through this chain rule. Again, this is like coming from basic calculus. Now, chain rule says that if you have to compute derivative of L with respect to X, you can break this into two steps. You can compute derivative with respect to Z, and then you can multiply that with the partial derivative of Z with respect to S. So this is a very standard chain rule in calculus, right? Now, how we can use this chain rule to train your neural network? And again, this is a very we need, I think, a couple of lectures to cover this. So we're just going briefly over this, but still let me know if this is not clear. So X is your input, Y is your input. Let's say this is your neuron or your network, which is represented by a function F. So it's taking X and Y as input, and it's producing Z as output. Okay, so this like could be a standard network. Now the forward pass is you take your input data, so these will be your features, and you pass those values to your function, and depending upon your kernels or whatever you have inside your network, there will be like some processing, right? You will compute the activations, and finally you will get the output. So this whole process of going from data to the prediction is called forward pass. You're starting from the left from your data and finally getting the prediction. So you're actually performing all the filtering operation inside your network. So this is forward pass. And in this case, we are not training anything. We are just trying to figure out if this is the input, what exactly our network is going to predict. Okay, so that's forward pass. The second step is called backward pass, and this is exactly when we train our network. Okay, so what is happening here is you do this forward pass. Again, you have the Z. Then depending upon the loss function, you can compute like whether the network is doing good or it's doing bad. You will have some function there, right? Then what you do is you can compute the derivative of your loss function with respect to Z, which is like the final output. All right, so that's the gradient like at the final layer, and using that you can update the parameters in the previous layer. So that's just one step. Okay, and that's like basically the gradient descent we just saw. You compute the gradient and you move towards the slope to find the local minima. So that's exactly what's happening here. So that's one step. But now the question is, if we have to update like the parameters in the previous layer, how will we compute the gradients, right? Because loss is like all the way at the end here. So what we can do is we can find the gradient, and in the backward pass, we backpropagate these gradients to the previous layers. So in this case, if we have to compute the gradient of the loss with respect to X, we know this chain rule, right? We can compute the derivative with respect to Z, which is like the intermediate variable, and then we can compute the partial derivative with respect to X. So that's exactly what's happening here. So then this first term here, which is the partial derivative of loss with respect to Z, we compute it right here. We can do that, right? Because the loss is actually a function of this variable Z. So we have the first term. Now to get the second term, again, we know that Z is a function of X. That's how we get z. So then we can compute partial derivative of this z with respect to x, and then that will give you the partial derivative of loss with respect to x. And similarly, you can do that for like all the previous layers. You just keep backpropagating this loss. So this is called the forward pass. This is called the backward pass. This is like when you are doing inference, you are making predictions. This is like something when you are training, when you're actually training your network. So when you backpropagate these gradients, then you know that formula, right? How to update the value, which will allow your values to go towards the local minima. So we perform that step for each of the variable in your network. And for that, you just need the gradient. And gradient, you can use the chain rule. So that's called the actual training. So this is like the step where the actual training is happening. And this is actually updating the kernels. Okay, so question from Anshuman, forward pass same as inferencing. Yeah, that's true. Okay, so that's like at a very high level how the network training works and why chain rule is very important. And this, I think we just discussed how it works, right? So it's showing like both the forward pass as well as the backward pass. And again, you can compute like these partial derivatives and go backwards, which is fine. But a few important points here. If you have an add gate, let's say you are adding two numbers and then you get a third number. So in that case, the gradient will be distributed among those. And the reason is like, it's simple. It's based on derivative. If you have x plus y equals to z, and if you compute the derivative, you will get contributions from both the parts, right? And again, max is something you just backpropagate the gradient, the value to the value which you picked. The values which you ignored, nothing will be backpropagated. And multiplication, you will switch the gradients. And again, these are just like coming from basic your differentiation rules. So this is like if you compute the derivative of xy, then you fix your y, then you find derivative for x, right? But the other one is like you fix x and derivative of y. So in that case, you're actually switching. So, but this is fine. You just have to know this. You don't have to code this because all of that is already there in the frameworks which you're going to use for deep learning. Okay, but it's good to know. Okay, so yeah, I think I have a very interesting demo which I think we can cover today. And Matt actually created this. Let me see. Okay, so can you see my screen? Okay, great. So, all right, so this is the current training set, and we are training for, let's say, ZOR is too complicated. Let's train for AND. I hope it works. It was working a while back. Yeah, I think there is some issue. Sorry about that, but it was a pretty cool demo. It was showing in real time, like how your network weights are getting updated as you train your network. But it seems like there is some issue in the backend. Sorry about that. So that's fine. We can continue. Okay, I hope you can see my slides again. All right, so that was gradient descent, but now the issue is we usually train our network on a very large number of samples. So if it's like image classification, it could be million samples. And you have seen that when you compute like the loss function, you take the average loss, right? So that loss is averaged over all the samples. But fitting all the samples into memory at the same time, it's not possible because you can't really fit like 1 million images at the same time, however big your memory is. So what you do is we actually take few samples at a time, and we call that as a batch. So we take a small batch, let's say 16 samples, and then we train for those 16 samples. So that loss is computed or averaged over those 16 samples. We train the network, and then we take like a next batch of 16 samples, again train it. So we keep doing that until we like have gone through all the samples 1 million. And this whole process is called one epoch. All right, so which means that we have seen each sample once, and then again we repeat this process. We train for multiple epochs. So sometimes depending on the data set, we train for 100 epochs, 200 epochs, sometimes maybe 10,000 epochs, right? So we keep training. So stochastic gradient descent is we don't look at like all the samples at once, and we call that like mini batch gradient descent because we are taking a subset of those samples. Okay, so that's called batch size. And so when we discussed that gradient descent, right? So when I showed you that curve, so what we did is we started from a random point, and then we compute gradient, and then we started moving towards the minimum. So similar to that, what we do here is when we design a network, so the weights of the kernel, we initialize them randomly, because that will give you like a random point in your loss curve, and then you will start from that point onwards. So your initialization is always done randomly. And then there's a parameter, this gamma, which is called learning rate. So if you remember, like the steps we were taking while we were going to the minima, so there was a coefficient gamma, right? That determines like how big your step will be. So that's called learning rate. So it's a very important hyperparameter when you train your network. And most of the time you'll have to fine tune it to make your network converge better. So this is a very important parameter you should know. And by now you should also know what it means. All right. So what you do is while you're not at minima, which means that your loss is not converging, your loss is not zero or it's still converging, you shuffle your training set, and this is like a normal training process. Then you take a mini batch and you perform gradient descent and keep repeating this process until you're satisfied with the performance or you are at the minimum, your loss is not converging any further. Okay, so that's the training step. And this whole process, when your network has seen one sample, that's called an epoch. So these are some of the terms which you should be familiar with. So this the number of samples you are taking in one mini batch, that's called batch size. That is also very important because for some of the problems, having a very big batch size actually helps. Okay, so now when you train your network, then it's a good practice. I think there's a question from Amir. When possible, is it preferable to choose a big batch size rather than small batch sizes? I mean, if we have GPU with a large memory, for example, does a bigger batch size necessarily work better than smaller batch sizes, or it's not always true? Yeah, it's not always true, and it depends upon a lot of factor. And a general case, when you have a very large data set and you have a large number of classes, then ideally the bigger the batch size, the better, okay, because it will be like giving like a lot of variation to your network. But for example, if you have a very small data set and then the number of classes are also not very high, then taking like all the samples at once, you might be like going in just one direction when you try to minimize your loss, and that always doesn't work that good. So then you'll have to limit your batch size, maybe taking a smaller batch. So that's one thing. The other thing is it also depends upon like what kind of loss function you're using. Okay. Sometimes like for some of the losses, very high batch size actually doesn't work that well. So there are many factors to that. But usually most of the times, I think in standard problems, the bigger the batch size, the better it will be. All right, so I think these are now details about the training process, and let's end it here and continue this in the next lecture on Thursday. All right, and if you have any questions, I will take those. Question from Fernando: would it make a difference if we do random sampling versus purposely giving samples of one class at a time? Yeah, you always do random sampling. If you are giving like samples just from one class, then the optimization will be just focused on that particular class. So the the curve will move in a direction which is good for that class, right? But then in the next epoch or in the next iteration, when you see samples from different class, then it might go in a different direction. So then your curve will not converge very well. So ideally you should have like all samples from most of the classes to make like a good educated guess like in which direction your network should go. Okay, question from Daniel. Will we be discussing training from a probability standpoint, that is trials, posteriors, log likelihood? See, I think that will be out of scope for this course because this is mostly like focusing on computer vision, right? So that will be like, I think, good from machine learning point of view, but I don't think it will be a good fit in this course. Okay. So Daniel, if you're interested, I think we have a machine learning course which actually talks about all those things. All right, so if there is no other question, let's end it here and enjoy your day and let me know like via email if you have any questions. Bye.